Good afternoon, everybody. Myself, Ram Singh, Assistant Professor from PSBTE&IT Leragaga, and today I am here to deliver a lecture on induction machines, basic introduction, principle, equivalent circuit of the induction machines, and moreover we will discuss about the starting of induction motors and about speed control of induction motors, how to start, what are the various methods of starting of an induction motor and various methods of control of speed of induction motors. In the today's lecture, the basic things we are discussing is induction motor construction. Next topic is basic induction motor concepts, the equivalent circuit of an induction motor. Then we will proceed to power and torque in induction motor, what the concept of power and torque in induction motor is. Then we will discuss about induction motor torque speed characteristics, variations in induction motor torque speed characteristics, starting of induction motors, speed control of induction motors, and some important features. At the last we will discuss about the induction motors, what the important features are there in an induction motor. So, all these topics we covered in today's lecture, starting from very basic of the induction motors, about the construction, and then about the basic induction motor concepts. Then we will proceed to the details of the induction motors, and then at the last we will discuss about the starting of an induction motor and speed control of an induction motor, and then the important features of induction motor. In part 1 we are discussing about the 3-phase induction motors. In introduction, if we say that a synchronous machine are those machines which do not run at synchronous speed. Most AC motors or induction motors favored due to their ruggedness and simplicity. In fact, 90% of industrial motors are induction motors. By induction motor we mean that the stator windings induces a current which flow in the rotor conductors like a transformer. As the name indicates, the induction motor, in which the working principle is based on the induction of EMF as in case of transformer. Induction motor may also be called as asynchronous motor or asynchronous machine. So, the motor which never runs on synchronous speed is known as asynchronous motor or induction motor. Working principle is very similar to the transformer. As in case of transformer, the primary winding is there, secondary winding is there. Similarly, the stator and the rotor of an induction motor are considered to be primary and secondary windings of the motor, similar to the transformer respectively. Next is overview of 3-phase induction motor. Induction motors are used worldwide in many residential, commercial, industrial and utility applications. Induction motors transform electrical energy into mechanical energy. It can be part of pump or fan or connected to some other form of mechanical equipment such as winder, conveyor or mixer. This figure shows the cutaway view of a modern induction motor. This shows all the parts of an induction motor, starting from this is the shaft of the induction motor, and outside it, this cut view shows the stator of the motor. This is the inward is the fitted rotor of the induction motor. This is the terminal box, outer body of the induction motor, and this is the hook for lifting the motor. These all showing the parts. This is the base of the induction motor. This cutaway shows all the parts in the induction motor. This is the figure which is showing the induction motor. The induction machines may be classified in many ways. The classification is on the basis of rotary or linear motor, 3-phase or single phase motors, wound or cage rotor. Rotary, if the motor is rotating in some direction, that is known as rotary motor, or not rotating in a particular direction, that moves in a linear motion, linear movement takes place, then that is known as linear motion. And according to the system of supply to the motor, whether it is 3 phase or single phase. The motors may be classified as 3 phase supply motors or a single phase supply motors, or a 3 phase induction motors or single phase induction motors. And as per the rotor used in the motor, whether it is phase wound rotor or whether it is squirrel cage rotor, the motors may be classified as wound or cage rotor motors. Next is the construction of induction motor. This shows the enclosure of the induction motor, stator of the induction motor, and this is the rotor of the induction motor. This is the terminal box of the induction motor. The three basic parts of an induction motor or AC motor are mainly rotor, stator, and enclosures. The stator and the rotor are electrical circuits that perform as electromagnets. Stator and rotor are both the electrical circuits, and similarly as in case of transformer, primary and secondary having no direct electrical connection, only magnetic field is induced and power is transferred from one circuit to the other. Similarly, in case of induction motor, no direct electrical connection is there in stator and rotor of the motor, but as per the electromagnetic Faraday's law, electromagnetic induction, power is transferred from one circuit to the other. An induction motor is composed of a rotor known as an armature and a stator containing windings connected to a polyphase energy source. Next is the construction. Basic construction of the rotor may be of two types, that is squirrel cage and a wound rotor. The rotor is the rotating part of the electromagnetic circuit or the rotating part of the motor, and stator is the stationary part of the motor. The rotor may be classified as or categorized as squirrel cage and wound rotor. The most common type of rotor is squirrel cage rotor. Induction motor types. Squirrel cage type rotor winding is composed of copper bars embedded in the rotor slots and shortened at both ends by end rings. Simple, low cost, robust, low maintenance. These are the properties of squirrel cage type rotor, that it can be composed of copper bars embedded in the rotor slots, and these are the bars which are shortened at both of the ends by the end rings, and this is the simple construction of the rotor. Cost is very low, robust in nature, maintenance required for this type of rotor is very low. Wound rotor type, rotor winding is wound by wires. The winding terminals can be connected to external circuit through slip rings and brushes. This is the other type of the rotor, and it is easy in case of control of the speed of induction motor, and cost is somewhat more than the squirrel cage rotor. So, these are the important points about the construction and properties of the two types of rotors. The main parts of the induction motor can be given as the stator, the rotor shaft with bearings, the stator frame with bearings, the cooling system, the terminal box. This is the figure which shows the stator of an induction motor. This is the winding. All the conductors are inserted in the slots of the stator, and these are the three terminals taken out from the winding connections to connect with the main supply. This is the enclosure of the motor. Inside there would be a rotor which would be rotating in the space given here. This is the stator of an induction motor. This figure shows the coils in the rotor, coils in the stator of an induction motor. This is the construction of squirrel cage rotor. This is a skewing slots, skewed of the slots is there, and this forms the construction of rotor like a cage of a squirrel. So, that is why this is known as, this construction is known as squirrel cage rotor, squirrel cage rotor. A wound rotor with slip rings. This shows the slip rings, 3 slip rings are used here on the shaft. The rotor is mounted, and this type of rotor is known as phase wound rotor or simply wound rotor in an induction motor. These are the close view of the slip rings. 3 slip rings are used each for each phase. 3 phases are there, 3 slip rings are there to collect the current, to supply the current. Slip rings are shown in this figure. Constructional features of squirrel cage and wound type motor. Stator. In case of stator, the stator consists of a stator frame, core and stator winding. And what the stator frame is? It is the outer body of the motor used to support stator core and windings, and also to protect the inner parts of the machine. The frame may be die cast or fabricated. Stator core. The stator core is assembled of high grade, low electrical loss silicon steel punching. The thickness varies from 0.3 mm to 0.7 mm. The laminations are used to reduce eddy current losses as in case of transformer. The laminations are slotted on the inner periphery and are insulated from each other. The insulated stator conductors are placed in these slots. Stator or field winding. The stator conductors are connected to form a 3-phase winding. The 3 phases of the winding can be connected in either star or delta. Next is the rotor of induction motor. The rotor comprises of a cylindrical laminated iron core with slots on outer periphery. The rotor conductor are placed in these slots. The laminated cylindrical core is mounted directly on the shaft or a spider carried by the shaft. There are basically 2 types of rotor constructions, as already we have discussed that these are the 2 basic types of the rotor constructions. Squirrel cage, no windings and no slip rings are provided. In case of wound rotor, it has 3-phase windings, usually star connected, and the winding ends are connected via slip rings. Squirrel cage rotor. In cage construction, rotor conductors in the form of bars made of copper or aluminium are placed in the rotor slots parallel to the rotor shaft. The rotor bars are short circuited by end rings of same material at each end. The rotor slots are not parallel to the motor shaft but are skewed to reduce magnetic locking of stator and rotor, and also to reduce the humming noise while running condition. So, the shaft or the rotor slots are not very parallel to the shaft of the motor, but these are skewed to reduce magnetic locking of stator and rotor, and also to reduce the humming noise while the motor is running. This is the particular special point to be noted here. Squirrel cage rotor of induction motor. This has been shown the copper or aluminium bars of the aluminium or copper material. These are the copper or aluminium zinc rotor core. This is the rotor core. This is the figure which shows the squirrel cage rotor of induction motor. Squirrel cage rotor, a schematic diagram has been shown. These are the 2 ends which shows that the all conductors are short circuited by this type of material. On the other end, the same conductors has been shortened by the same material. These are the conductors which has been placed in the slots of the rotor periphery. These are not parallel to the shaft of the motor to avoid the locking of stator and rotor, as well as to avoid the humming noise of the motor during the operation of the motor. Wound rotor. The rotor is wound with an insulated winding similar to that of the stator. The rotor winding is always 3-phase winding. The winding may be star or delta connected, but star connections are usually preferred. The 3 terminals of star connections are brought outside the rotor and connected to 3 slip rings. The carbon brushes are pressed on the slip rings. External resistors can be inserted in series with the rotor winding for speed and starting torque control. In case of wound rotor, we can insert the external resistance for starting purpose as well as to control the speed of the motor in running conditions. This is a schematic diagram of wound rotor of induction motor, connection diagram. In this we have shown that the winding is connected in star manner, and these are the 3 slip rings which has been connected with the winding, rotor winding, wound rotor, slip ring of induction motor. Here we can insert the resistances, external resistances in series with each of the phase to control the speed of the induction motor as well as to start the motor. Differences between squirrel cage and slip ring induction motor. What the difference is between the two motors? Squirrel cage induction motor is simple in construction, but slip ring induction motor is complex in construction. Slip ring induction motor is having higher initial cost, but this squirrel cage induction motor is cheap in cost and more reliable, maintenance free. In case of squirrel cage induction motor, less need of maintenance is required, but in case of slip ring induction motor, more maintenance is required. Its working can adjust itself to only numbers of stator poles, and both the stator and rotor windings must be wound for the same number of poles. Starting torque cannot be controlled, starting torque can be controlled. So, this is the basic points on the basis of which we can differentiate between the two motors, squirrel cage induction motor and slip ring induction motor. Next is the principle of operation of induction motor. Operation of 3-phase induction motor is based upon the application of Faraday's law and the Lorentz force on a conductor. If a short circuited conductor is placed within a rotating magnetic field, an EMF is induced in the conductor due to electromagnetic induction, and due to this EMF, current starts flowing in the conductor and sets up its own magnetic field. Due to the interaction of these two fields, a torque is produced and conductor tends to move in some particular direction, and direction of that conductor, in which direction that would be moving, depends upon the direction of the main magnetic field. So, this is the electromagnetic induction, which is the principle of induction motor. How rotor rotates? A 3-phase induction motor have a 3-phase distributed winding. When we give supply to stator, then a rotating magnetic field produces, which rotates at synchronous speed. The rotating flux cuts the rotor conductors and EMF produced in them. Because these conductors are short circuited, so current is produced in conductors. So, rotor MMF is produced, which produces synchronously rotating rotor poles. So, this is the method how the rotor rotates in the space. This is the production of torque, in which way the electromagnetic induction works in the motor, how the motor starts to operate, how the rotor starts to rotate in a direction. These are the various figures A, B, C, D and E. These are the various 5 figures which shows the production of torque in an induction motor, how the torque is produced. At the very first figure, in A figure, these are the shown rotor conductors. This is the rotor, this is the stator, and rotation of field is shown in this direction as by this arrow, and then flux direction is this in this arrowhead direction, and motion of conductor relative to field is shown here with this arrow. Direction of induced EMF has been shown at dotted, and due to this direction of EMF induced in the stator, this conductor experiences a force that would be shown in the D figure. In this way, this cuts the conductors, and rotation of field in this way, and the rotor speed takes place in the same direction, and flux is here in this direction. Force on conductor takes place like this. Direction of current is shown in this figure. So, this is the way how production of torque is possible in an induction motor. Next is stator equivalent circuit. Equivalent circuit, we are now discussing in brief the equivalent circuit of an induction motor. figure shows the stator equivalent circuit for a polyphase induction motor, and this is the R1 X1, mean to say the resistance and the leakage reactance of a stator, and this is the RC and XM, magnetizing component of reactance, and this is the resistive component of the reactance resistance. This is very similar to the transformer. V1 has been applied, E2 has been induced EMF, this Im is the magnetizing component of the current, this Ic is the working component of the current, this I phi is the total amount of the current flowing in this branch. This is the amount of current I2 to this direction. This is the stator equivalent circuit of a polyphase induction motor. Equivalent circuit of the rotor winding. Now we can show the similar in this similar way the equivalent circuit of rotor winding. This is the EMF induced in the rotor winding, that is S times of rotor EMF ER, S times of rotor EMF ER, that would be the voltage available at the rotor input terminals. This R2 is the resistance of rotor conductors, JSX2 is the reactance of the rotor conductors at any slip value S. And then in the V figure we can write this JX2 as JX2 reactance and this resistance as variable resistance with the change in value of slip, that would be variable resistance R2 by S. And then we can write it as R2 JX2 resistance of the rotor conductors, reactance of the rotor conductors, and this would be the variable resistance with respect to the value of S, slip value. As the slip value changes, the resistance of these conductors changes, R2 into 1 minus S over S. This is the equivalent circuit of rotor winding of an induction motor. In the previous slide, we have shown the equivalent circuit of the stator winding of the induction motor. So, we can combine the both of the equivalent circuits and we can obtain the final equivalent circuit of an induction motor, that would be like this as shown in this figure. It would be the combining of both equivalent circuits, circuit for stator as well as circuit for the rotor. This has been shown that this is the total voltage applied V, this current in the stator winding I1, this total current in the rotor I2, R1 JX1 is the resistance and reactance of a stator winding, or we can say that impedance of the stator winding. This is the impedance of the rotor winding, and these are the two branches of the current which is divided into working and magnetizing component of current. This EMF is here across these two terminals E1. And now we are defining slip. What is slip? We have discussed that slip is changing, resistance is changing, and what the slip is? That can be defined as the difference between the synchronous speed and the rotor speed, and the percentage of that difference is known as percentage slip. Simply, if we say that slip S is equals to Ns minus N with respect to Ns, where S is the slip, Ns is the synchronous speed in RPM, and N is the rotor speed in RPM. So, this S is equals to Ns minus N with respect to Ns. How much is the speed difference is there, actual speed, how much differentiates from the synchronous speed with respect to synchronous speed, that would be the slip value, and if we multiply this factor with 100, that would be the percentage slip value for the induction motor. This is the slip rings and brushes in an induction motor, slip rings and brushes in induction machines. This is the sliding contact winding on rotor, slip rings fixed to start, and this is the rotor shaft shown here in this figure. These are the brushes, stationary terminals, sliding contact of the slip rings. At no load, the slip is nearly 0. At no load, the slip is approximately 0.1%. At full load, the slip for large motors rarely exceeds 0.5%. For small motors at full load, it rarely exceeds 5%. The slip is 100% for locked rotor. When locked rotor condition is there, or we can say that at stationary condition or locked rotor condition, the slip value is 100%. Frequency induced in the rotor. How much frequency is induced in the rotor conductors? The frequency induced in the rotor depends on the slip, and that can be given as Fr is equals to Sf, where in this expression Fr is the frequency of voltage and current in the rotor, F is the frequency of the supply and stator field, S is the slip value. So, this rotor frequency is the S times of frequency, standard frequency, into slip value S times, that would be the rotor frequency in the rotor conductors. Next is the torque slip curve. For an induction motor, we can draw the torque slip curve likewise this. This is the braking region of the motor, this is the motor region of the motor machine, induction machine, this is the generator region. On x axis we have taken the speed in percent of synchronous speed, percentage wise speed, and the second value we have taken as slip as a fraction of synchronous speed. Slip value on y axis we have taken the torque for motor in this half quadrature, and this is the torque for generator in this quadrature. So, this is the from this dotted line to this dotted line, this is the motoring action, and from this dotted line to this dotted line, this is the generating action, reverse of the motoring action. As we know that action of motor is reverse of that of the generator. So, this curve shows the torque slip curve for induction machine. We can say that for induction motor for this curve, and that is this curve is for the generator action. This induction machine is about the torque slip curve showing braking, motor and generator action. Harmonics in induction machines, time harmonics are there. These affects torque and causes considerable heating in the machine and are hence a cause for concern. These harmonics are called time harmonics since they are generated by a source that varies non-sinusoidally in time. The second harmonic type in the induction motor is space harmonics. The space harmonics are a result of non-sinusoidal distribution of the coils in the machine and slotting. These have their effects on the speed, torque and current of the machine. This is the curve which shows the effect of harmonics on loaded machine. This is the curve which shows the effect on the loaded machine, what the effect of harmonics having. This is the power flow diagram of the induction motor. We can understand that how we give the input to the induction motor, how we take the output from the shaft. This is the total active power to stator, PE, total electrical power is given as input to the motor stator, and here in the stator there are I square R losses and iron losses in the stator of the motor, and then output of that stator after losses is taken as the active power supplied to the rotor. How much power is supplied to the rotor? From that we reduce the or we deduct the I square R losses in the rotor conductors, then total mechanical power developed, then minus of that windage and friction losses, and finally shaft power is taken as output of the motor, that is represented as PL, shaft power. This is the mechanical power developed PM. This is the I square R losses, iron losses, PIR. These are the I square R losses PIS in the stator, iron losses PI. Air gap power. What the air gap power is? Air gap power is the power transferred from stator to rotor across the air gap. How much power has been transferred from stator of the motor to the rotor of the motor across the air gap? This can be written as, can be given by this expression that PG is the air gap power is equals to 3 I2 square into R2 by S, where this I2 is the rotor current, PG is the air gap power, R2 is taken as the rotor resistance of the rotor conductors, S is taken as the slip value of the motor. Shaft power is the output power, total available power at the shaft, and this power SH, PSH power at the shaft or PG is equal to PG minus rotor ohmic losses minus friction and windage losses. This is the shaft output power. Operating torque, torque from light load to full load conditions. Starting torque can be defined as torque at start when slip is equals to 1. Breakdown torque is the maximum torque that motor can develop. If motor is loaded beyond this torque, the motor will decelerate and come to standstill at some time. This is the torque speed or speed torque characteristics.